we discussed linear discrimination and also logistic discrimination, and we wanted to like identify, instead of learning the posterior probabilities and all the likelihoods, we just wanted to basically find a line that separates classes. And we basically looked at it in a geometric way, where on the one hand side of the line you would decide to have one class over the other, and we identified that we need to come up with basically the parameters that define these separations or these discriminant functions. And the main point that I would like to emphasize again is that most of the time in machine learning you don't really have an analytical solution to this problem, and which is you want to find the optimal set of parameters that reduce like your criterion function or your error function the best, and basically give you the minimum of the error that you have on a given training set, with capital X there. And well, since we don't always have this guarantee, we need to come up with a way to find those parameters. And the idea that I wanted to highlight on Monday was that the error function of the criterion function is basically a surface in multidimensional space that is dependent on all of the parameters of my classifier or approach. In a linear discriminant case, for example, it's the number of dimensions you have as input plus a bias, so you can move it away from the origin of the Cartesian system. And so, but for high-dimensional classifiers or more complex classifiers, we can't really visualize this, but we're gonna again revisit one of these visualizations. But in general, you are situated somewhere on this surface because you initialize your weights with a certain like random number for all dimensions, and you end up at a predefined kind of spot for your training set. And that's basically the start point that you have, and we identified that in order to reduce the error, we need to find a way from where we are to the minimum of this surface of the error function. And the idea here is that you walk down the gradient or down the hill into the valley, which is achieved through the so-called gradient descent, which is basically just shifting the weight. So this is the delta Wi, which basically updates your Wi, which is the one of the weights that you have in your classifier, and it shifts it into the negative direction of the gradient, which is calculated as a partial derivative with respect to the Wi that you want to update. You have to do this for all of the parameters that you have. So let's say if you have like 2 parameters, you need to do 2 of these. If you have a neural network, you need to do this for every single connection. Okay, and we're going to come to that today. But that's why I want to highlight this again. And then you don't walk the entire gradient, because that would be too much, but you walk a tiny bit. And that's this eta, and usually this eta is like anywhere from, I don't know, like sometimes it's 1 even, so that's fine, like that's the entire gradient that you walk down, but sometimes it's even like, I don't know, 0.00001 or something like that. And it depends on really how jittery or how how sensitive your error surface is. If it's very smooth, you can walk far, right? Like with one step. But if it's like really, like if you might miss a tiny valley, then you don't want to adapt the weights too much at every single time. So how does this look like? Well, this looks like this. Basically, you initialize your weights, theta 0, theta 1, and you end up somewhere on this surface. So you can see from 0 to 1, you can end up anywhere, and you randomly initialize that. You can end up here, you can end up here, etc. So for a given training set, it is predefined, so to say, with your initialization where you're going to end up at. Okay, so that's defined. Like you're going to have some certain error if you initialize your weights with something like randomly. Okay, and what you want to find is this place here where it's the optimal solution. So what you do is you start up here, and then you identify what the gradient is, and well, the gradient goes in this direction, or like actually goes up the hill, but you walk down the hill, so in the negative gradient direction, so you move closer and closer to a minimum value, okay? So this solution gives you an iterative process that always reduces your error, okay? It always goes down. However, depending on your starting location, it might not go to the optimal solution, okay? And so it might end up in a local optimum rather than the global optimum. So that's important, okay? So we discussed that on Monday. We said like, well, you know, you can start at multiple locations, try it out multiple times and see where you end up at, and you take the best one. That is exactly what validation sets are for example. Like, you can, so you start off at multiple locations, you reduce your training error, but you want to actually know which one's the best for my validation set, so you test it on the validation set, you take the one that works best for the validation set, and then you test that on the test set, which you have never touched before, okay? So that's kind of like the way to do this. Alright, and for example, even if you start at the same location, it's not guaranteed that that you end up here all the time, because it might be because of your learning rate, you might end up somewhere else. Okay, so all the parameters influence this, not just the starting locations or the weights, but also the learning rate and a couple of other parameters, depending on the algorithms. Okay, so in some machine learning algorithms, you have parameters like these hyperparameters that we talked about already, which you don't learn, you don't update those over time. Okay, so they are set from the start. All right, so we had this nice visualization as well, where depending on where you start, you end up at a certain location. Okay, and then we walked through this example of logistic discrimination, where instead we said, instead of having like a line that we want to update or identify, we now have a d-dimensional sigmoidal function that has, like depending on the number of input weights, number of weights here, plus one weight. That basically gives you like a shift again. If that wasn't here, it would always go like through 0. Okay, and then we define our error criterion, or like our criterion function, basically as like this E dependent on this W vector plus the W0 given a certain learning or a training set, and it's in this case the cross entropy between what we predict what the output is in our logistic discrimination and what the actual output is for each sample t. So you go from t equals 1 to like the number of values here in x. Okay? Alright. So that's the basic idea. And then for us to be able to solve this problem, we said, okay, we need to do the partial derivatives to do gradient descent. And for that, this information here, where like 1 divided by 1x minus a is like it's going to be helpful that this is derived to that. Okay. All right. So basically, what we have to do now, in order to come up with our update functions, we need to take our error criterion and do the partial derivatives for each of the weights. And we don't have to do this for all of them because, like, well, we apply it to all of them, but we don't have to calculate the partial derivative for all of them separately because it ends up in the same. We can just say from J1 to D, What we see though is that, for example, all the inputs that are depending on other indices, for all i's that are not equal to j, they all fall apart, like they all fall away. So we only use one input dimension for the update. We look for each of those input dimensions if the predicted output is equal or different from the output that we want to have. So r is what we predict it is, and what y is what it is. Okay, and so you can already see. So if this is equal, that thing is not updating, right? But if it's not equal, well, we move whatever we are predicting. Are we like predicting a larger value or a smaller value? We're moving our weight, which is basically updated down here, in the direction of x. Okay, and this is also important for perceptron learning. We do exactly the same there, where basically what we call this is a delta learning rule. So there's a difference between the target and the predicted value. That's the delta, and then based off of the delta, we adapt our weights towards the input. Okay, and that's done for all of the j's. And then for the w0, well, it's even a bit easier because all the x's fall away. So that's not dependent on the input at all, so we just move it towards the direction that we want it to go in. Okay, so if this is larger, well, then we move in the negative direction, but we have the multiple minuses that x each other out. Okay, all right, very good. So I hope that makes sense. And then we also have this written down as an algorithm that might be a bit easier to implement than these, like basically you just have to implement these two functions. All of this is just prior work that you have to like do before you can build your machine learning algorithm. All right? So that's just an example, and we're going to go into more complex partial derivatives for neural networks, where it then becomes clear that for example, multiple layers, you are dependent on what the error is of the other layers so that you can move it through the network. Okay? All right. So that was that. And then we went on to discuss neural networks. And we started off with discussing biological neural networks. And in this case, we particularly focused on the neuron itself. So we have a neuron here with the soma and the center of the neuron, its axon where the information is transmitted from the neuron to the other neurons, and the dendrites where the neuron is gathering information from other neurons to compute inside here. And we talked about synapses, and those synapses in biological as well as in simulated neural networks can both be excitatory or inhibitory, which means they either excite the neuron to create an output or inhibit the neuron to create an output. And this is exactly what we're also going to simulate with connection weights between a prior neuron and the neuron that we're simulating right now. And basically, if we want to have an excitatory connection between the two neurons, we have a positive weight, and if we want to have an inhibitory connection between the two neurons, we just have a negative weight. And that's kind of like the clue here, okay? And another thing that we talked about with this graphic here is that it is not just that the neuron doesn't compute everything by itself, but it gathers information from others, so that's the spatial integration of information. But then also it doesn't integrate information just once, but it also takes input from a longer time period. So it's also temporal integration. So it's a spatio-temporal integration before we produce an output. And this is really what we want to discuss with the basic neural model. And we talked a little bit about how action potentialists submitted, but thankfully we don't have to model all these complicated things in our simulated neural networks because we want to have like large neural networks and with limited computational power we can't really do that very well. So we reduce it to first of all this basic neural model, and what you can see here are the following things. So first of all, X, that's basically the external input that comes in from the outside world, maybe light, maybe sound, and so on. So this is input from somewhere else. It might be leakage, electricity, or like potential that comes into the neuron from somewhere else. But then we also integrate information over all the neighboring neurons that we're connected to. And these are n different types of neurons. Okay, so we have n neurons that are connected to this neuron, and we need to integrate all the information over them. So we create a sum, okay? And then how do we model inhibitory and excitatory connections? Well, we use the C parameter here, which basically gives us the weight between the neuron I and the neuron J. And here we're simulating neuron J, so neuron I is basically iterated here, so that goes over all the neurons. And then we have Y here, which is basically the output of the neuron. So YI is the output of the other neuron. And it's dependent on T, so that's time, right? So we have T here, which is the current time that we're investigating, but we have then this minus Dij. Okay, so what was that? Well, we said it takes a little bit of time until the information comes to this neuron, so that's the difference between the time when this was processed and when the information for this neuron arrives, okay? All right. In most of the simulations with these kind of neurons, this basically would be 0. So what that means is just that we have a takt synchronization between all the neurons, so they produce stuff at the same time all the time, okay? So there's no lag between them. That makes it a little easier for us to compute, okay? But just for completion, we have that here. All right, then I said, well, this is then the spatial integration, right? So we are integrating information over different neurons. Where does the temporal integration come from? Well, the temporal integration kind of comes from the fact that this is a differential equation, and we basically want to update our new value of the membrane potential, the potential that the neuron fires or the neuron produces an output, based off of basically the derivative of the old one plus this external input. And the entirety here is kind of like considered as external input, but we are integrating over time with the previous times differential potential of the membrane here. And we discussed that before. So if we have a function and we take the derivative of that function, it becomes the function again, and we know it's the exponent. So this basically means that this temporal integration, and it has a minus, kind of loses potential exponentially over time. So it goes down to 0 very quickly. So if there's no excitation for this neuron, it forgets very quickly. And then we said, well, if this is basically allowing us to give, or like has some temporal information that is present over longer periods, so you have basically memory over what happened before. That means basically that this neuron actually does have factual memory. Okay, if we remove this part, it doesn't have memory. It's just a neuron that always processes the information that comes in from outside and from the other neurons. The good news is, usually we never have memory. Okay, so in the beginning we're just gonna remove that for the time, and all the basic models do not have information of what happened before. We're going to come to models towards the end of this lecture. Really briefly, but then also towards the end of the entire class, at the end of the semester, we're going to talk about neurons that actually have long-term memory and can utilize that. Okay? And then, like, one hint already is the fact that this memory goes down exponentially. That also kind of gives you a hint that like standard neural networks like these would not be able to learn long-term dependencies. And there is this new interest in deep neural networks that actually have the potential to learn these long-term dependencies, and those we can discuss at the end of the semester. All right. So before we move on, I need to also then now talk about what the output of the neurons are. So we said like the output is defined as this y, but then basically what this y is the membrane potential at time t that is fed into a transfer function. And a transfer function is nothing but something that takes a potential and transfers it into something else. And the easiest thing would be to transfer it into itself. Okay, that's totally fine. A lot of the neurons that we will use just do that. Okay, so that's very easy. The other option would be we have a sigmoidal function which basically goes from 0 to 1 with a certain steepness parameter that you can also validate for. You can use your validation set to find an optimal beta here. Or the tangents of Hyperbolicus that basically goes from -1 to 1, which is also a legal and fine transfer function. There are other transfer functions that we're going to talk about, which are, for example, the Heaviside function, which is 0 until you reach a threshold, and then it's 1. That's fine. Then there's also a new one that people often use nowadays in deep neural networks, which is called the rectified linear units, which are basically 0 until you reach a threshold, and then it's the value. So it's first 0, and then maybe you reach the threshold here, and then becomes a linear function. That's valid, okay, as well. And so there are many, many different types of transfer functions, and here are just a few of them that we will use. Okay? All right, so we talked about this, and the good news, again, is for machine learning, we use even easier neurons. Most of the fact, or the most important part is that we are going to get rid of this. Okay? All right. But this basically motivates how we come from the biological neural networks or biological neurons to artificial neurons, and like this really nicely motivates how synapses work and so on. One more thing that I should mention, again, I think I mentioned last Monday, is that these neurons don't spike, so they don't produce spikes of that go along axons, but they fire at rate. So these are ratio or rate neurons. So basically, so for this one, the neuron wouldn't fire at all, the neuron fires at half strength, the neuron fires at full strength, and so that's kind of like how you can interpret that. Alright, so let's simplify this a bit more. So the simple neuron model, and we are going to use this notation most of the time, looks like this. We have an input vector. At each of those locations here, we have a weight vector, which are these inhibitory and excitatory connections between input and the synapses, okay? And basically this input vector can come from anywhere. In this case it comes from outside, so this is just the external input. There are no connections to other neurons. We don't have to bother about that. So what we need to do is we compute a dot product between the input vector and the weight vector, which is here. And then we can add a theta, we can also not add a theta. We can have, for example, always one input that is always on and has theta as a weight, so you can simplify that as well. But in general, so you basically compute a dot product, and then you look if the dot product is greater or equal a sum or below that. Okay, greater or equal a threshold or below that, and then you would produce either a 1 or a 0 as output. Okay, so that's the simplest model that we can come up with. And yeah, so so this is kind of like the basic idea. We don't model any previous membrane potential, so it doesn't have any memory. It integrates information only from an external input, but these could also be connections to other neurons. And then synaptic weights are stored in this C, which is in this case a vector. And you can already imagine if we have multiple neurons, this C becomes a matrix, and you do nothing but just compute the matrix multiplication. So that's really, instead of a dot product, you compute matrix multiplications, okay? So there's nothing really difficult about that. And the output basically is based on a weighted sum between the input and the weights, which is the scalar product. I heard that this is more of a German term. The English word, or more common English term, is the dot product. And so basically you just multiply each value with each other and you sum them together. And in this case, this is a threshold neuron, but we can apply any other neural function as well, or like transfer function as well. So this would produce 1 or 0. This will produce basically the weighted sum. Okay. So once now we can actually connect those neurons, and we can imagine that there is information coming from the outside, and a bunch of neurons process this information, and then they produce something that for those guys looks like it's coming from the outside. And you can reiterate that multiple times, so you can have many layered neural networks if you just combine those ideas that we just talked about together. Okay. So they can be organized in layers. Information is propagated through those layers, one step at a time, and so these layered architectures have huge number of application capabilities, and they're utilized very, very often in machine learning nowadays. And you have sometimes, I've seen like neural networks with hundreds of layers, and so I think that's a bit over the top, but like 5 to 10 layers is very common right now. So that, like, basically one of the things that we need to talk about today, and we're going to talk about this at length in a second, but what is important is that we only have, like, if we deal with these layered architectures, we only have knowledge of like what comes in, right, and what comes out at the end. We do not know what's happening in between. Those layers are hidden from us, so we do not know what's happening inside. Sometimes we don't need to know, so when we run the neural network, we don't need to know what's happening. But when we train the neural network, we need to basically access those layers and allow them to understand what they need to do so that they have a better performance afterwards, okay? And so, and then the output layer basically produces the output that we can then observe, okay? So, and this is just a slide for clarifying what I meant with, like, it has many applications. Well, so what can we use these for? Well, we can use those for classification. We can use those for approximation or function fitting. And like, that's going to be a fun fact about multi-layer perceptrons with continuous output, like the linear function output or sigmoid function output, these networks are actually universal approximators, so they can approximate any continuous function to whatever degree you want. So, like, you can overfit anything. That's the good and the bad news. So, if you have a too powerful network, you can overfit anything. So, yeah, that's as you know, like, good and bad at the same time. But that also means they're super powerful. Okay. I have seen and used neural networks to control robots, for example. So we developed so-called echo state networks, and we might be able to talk a little bit about this today, which are neural networks that are usually pretty small, that get continuous input, they know what happened before, so they actually are having a memory, and we use them to basically steer the robot's wheels so that we know how to move the robot back and forward and steer around a couple of obstacles. Then also, I don't think we're going to talk about this too much, but you can use neural networks to also store information, and there are neural networks called neural associative memories, which are kind of like my PhD supervisor's claim to fame. So he came up with that term, and he analyzed them mathematically and found out that you can actually, in neural associative memories, you can store more information than in just a binary memory where you store zeros and ones. In those, you can actually store more than a bit in a bit, or in like one weight, in 1, 0, and 1. Yeah, it's pretty cool stuff. But I don't think we're going to have time to talk about that. It's more of a fringe kind of thing, like nobody really uses them anymore. Alright, so let's talk about learning in neural networks. And we talked about learning before, I think in the first class, basically learning again is kind of like essential capability of humans to learn new capabilities, to gain novel knowledge, and to basically also store this so that you can recall this new knowledge after some time has passed. Okay? And so we are interested in the mechanisms that allow neural learning, and unfortunately, like the neurosciences is not like crazy advanced about this. Like there are many really good theories but it's not entirely understood. I believe, at least when the slide was made a while ago. But two main mechanisms kind of can be identified that allow us to learn in a brain or in a neural network. And the first one is, for example, basically to learn or to create new structures, new connections between neurons. So you basically have a network that grows, that learns new connections between neurons, that combines them, or it could remove them, if that makes sense. But you can already guess, well, in computer science we don't really like data structures that grow and get smaller, and so we would have to allocate all the memory until the maximum, and we don't really like that, so we're not going to do that. The other method is to basically change the pre-existing connection weights, and we simulate all of them, but then we basically allow the synapses to change their weights. And this is really the method that we're going to do. So we are updating in those simple neural networks, we're just going to update those C vectors. So we're going to update how the connection between one neuron to the other is weighted, or how the connection between the output or the input to the network is weighted. Okay? And learning is slower than the update mechanisms. So basically, that's just a kind of like a point to motivate why we have small learning rates. Okay, and not always update very quickly, okay? Yeah, and that's just a last point where all of this here, that like the learning, the adaptation of the weights, we do that before we actually deploy a neural network to like do its duty and to be to work or to have the application phase going on. That's just a hint at the nonparametric method that we discussed, the k-nearest neighbor method, where no training has been done until the application phase, because it's a lazy neural network, a lazy classifier that never gets trained, and these get trained before you apply them. Okay, so let's look at how we do this in a simple architecture. And again, as before, in supervised machine learning, we will need information about like what we want to achieve. Okay, so we need a target signal, a trainer that tells us what we need to do. All right, and so the main goal for us will be that the output of the neural network, which we denote as y, is always very close to that t value. Okay, and that's for all the samples in our data set. So we want to do this. We want to be as correct as possible for all the samples in the data set. Okay, so again, we start with the same neural net architecture. We add a new signal, which is the teacher, and the principal idea is basically through adaptation of these weights here, which are in this kind of column here, we would like to be able to move y as close to t as possible. Okay, and this idea that I also already mentioned for the logistic discrimination is basically used for the majority of neural learning, and also, for example, in the perceptron learning. And the function, or the idea here is that the delta learning rule is basically your new weight, which is the c vector in the next time step, is equal to the old vector plus, in this case it's a rho, before it was an eta, like a learning rate. You move it to the input x, and you only move it if you make a mistake between the target and the input, the output. Okay. So you decide: do I make a mistake? Yes or no. If this is like a binary neural network, it would produce either -1, +1, or 0. So if it is -1, so that would mean we subtract the input vector a little bit from the weight vector, and if it's +1, we add the input vector a little bit, so we move it away or towards that input. Okay, and we're gonna have a small simulation of this, but that makes this more intuitive. And then if this is 0, well, obviously we're not doing anything. Okay, so that's the main idea. All right. Good. And this basically again is. I wonder if I should show it. I'll do it in a little bit. I'll show you an animation in a little bit. So, and we talked about this already, kind of, where we was like, okay, how do we systematically construct these learning rules? How do we come up with new delta rules, right? And they all look very similar, in fact. And so, basically, what we do is we have our training set, which is defined of tuples between input vectors and target vectors. And in this case, they can be, they can be anything, right? Like you can either have a binary signal 0 or 1, but you can also have, like, this is not like reduced to that. You can have your classes coded as 0, 0, 0, 1 somewhere. If like you have one class out of 5 is correct, so this is called like a one hot vector. The one class that is the target class is 1. Before I confuse it too much, I'll probably have to write that down. So these t vectors could be something like this. So if you have like 4 classes, and this would mean, and this is for a mu, like this is for one sample, the third class is active, okay? And then you could make it the first class is active, and so on. And the cool thing is, this can be anything. It can be like 0.2 here, 0.8 here, 0.0, or like whatever. Most of the time you would want this to sum up to 1 or something like that. But it's really up to you how you define your target. So that can be anything again, like you can classify, you can approximate, and so on, okay? All right, and then we're basically looking for our network output for each sample mu to be about exactly the same as this t vector. And but we had that before. We need to define an error criterion or a criterion function to measure how close we are. Well, let's do the quadratic Euclidean distance, for example. We can do really anything here. We can again do the cross entropy if you want to, but basically you define your own error function, and then we basically want to minimize the error, and we know that the neural output y here is dependent on all of the vectors and all of the connections in our neural network. So what we want to do is we want to find the connection matrix, so this all the weights summed together in this big C matrix that minimizes this function, okay? So that's what we want to do, and because we can't really get a complete derivative for all the weights at the same time, we do that for each weight entry in this separately, so we do the partial derivatives as we had before. Again, optimization is most of the time achieved through gradient descent. Basically, yeah, so we need to minimize that. And in broad terms, what we need to do is we update the weight matrix with the old matrix minus a learning rate and the partial derivative of this, and to simplify that, obviously we're not computing that for the entire matrix, but for each entry separately. And yeah, so this is kind of how you systematically construct learning rules, okay? And all you kind of need to do is be able to differentiate this equation towards each of those weights, and we're going to talk about that in a second. But before we go there, I'd like to show one typical neuron that is a bit different to the linear or the simple threshold neuron that we talked about. It doesn't have this additional, well, it has like this theta function here, but basically this was one of the first neurons that was simulated. It's called the perceptron. It has inputs, it has weights, it does the dot product again, and you apply like a heaviside or a threshold function based off of a theta here, okay? And you can solve linearly separable problems where on one side of like this discriminant that we learn here, you have positive values, and on the other side you have negative values. Let's see some facts about the perceptron. So basically the perceptron tells you if there is a hyperplane or a line in the 2 dimensions, in 3 dimensions it would be a plane, in 4 dimensions it would be something more complex. So basically this algorithm finds a optimal separation. It finds a separation. It does not find the optimal one. And we can always find a solution for linearly separable problems. And this is, again, the learning rule, which is, you can see the delta learning rule, and the learning algorithm converges after finite many steps if there is a solution, and this is also expandable to perceptrons that learn multi-class problems, because you can basically reduce this problem to one versus many problems. And to visualize what is happening here in the delta learning rule for the perceptron, I brought a little visualization for that. Hope I can find it. Alright. It's always interesting to know which file we need to do here. Nope. Because these are flash animations, I never know if what. I think Chrome is now striking. Oh, come on, that always works. Very good. So there were security concerns. All right. So basically, whoa. It's almost like a Windows computer now. All right. So basically, what we have is 4 data points. 2 red ones, 2 white ones. We can move them around. Let's see, make it a bit easier, like white margin between the 2. Let's see what the perceptron learns. Basically, you can see the visualization of the perceptron down here. So you have the inputs that are going to be updated towards what these locations are, so x0 and x1. And then we have the 2 weights, and we're going to update those weights consecutively. Right now, I think the separation, or the hyperplane that the neuron thinks it uses is down here, so that's not good. Alright, so let's update that. And you can kind of see, well, I should probably reload the thing and do it step by step. Basically, what the neuron or the perceptron looks at is like this input right now. So this input is located here, and the weights are initialized with 1 and 1. The learning rate is 0.1, and I'll have to update the values, and basically this is the direction of where we have to update this value towards geometrically, and so we now have the new separation here, and then we look at this data point. We make a mistake because it's not on the right side of the separation, so we update the vector again to turn it around, and already now we look at all the data points iteratively, and nothing had to be updated because there was no error made. Okay? So let's reload this again, and let's see, for example, this is a little bit harder. Let's see, can it find the solution again? And you see, only for the red ones it updates it, because only those make mistakes. The white ones it doesn't make mistakes for, so it has to update for those, and it goes through them all the time until it doesn't make any mistakes anymore. And I think it has learned it now, right? Yeah, I think it's done. Doesn't really matter. I mean, like, it's not really updating anymore. Okay, so what happens if I have the learning rate of 1. And basically have a similar problem. So now I jump a lot more, okay? And it will find a solution, but it will take maybe a little longer, right? So the perceptron learning algorithm will always find a solution if there is a solution. Okay, let's make that there is, for example, no solution anymore. Okay, will it find the solution? Well, it won't, right? You can run this many times. It will always make a mistake. It will never find a solution. And this problem here is called a non-linearly separable problem. And those are, just so you know, not necessarily uncommon. I think you know one already. Basically, the XOR problem is impossible to solve with one single perceptron, so we need multiple ones of those. And you can maybe say, okay, like if you have 2 dimensions, you don't really have that many non-linear separable problems. Well, in 2 dimensions you have the XOR problem and the inverse of the XOR problem, so the not XOR or something like that. So that's only 2 out of 16 possible Boolean functions. Well, the percentage of linearly separable problems with higher number of dimensions gets reduced very quickly. So like the more complex problems really need to be solved by more complex systems, and the one neural network architecture that we're going to talk about that basically helps us solve these more complex ones is called the multi-layer perceptron. We can take a 10-minute break and then continue on that one.